In classical electromagnetism, the electric potential, i.e. or V, and also called the electric field potential or the electrostatic potential, at a point of space is the amount of electric potential energy that a unitary point charge would have when located at that point. The electric potential of a point may also be defined as the work done in carrying a unit positive charge from infinity to that point. The electric potential at a point is equal to the electric potential energy of any charged particle at that location divided by the charge of the particle. Since the charge of the test particle has been divided out, the electric potential is a property related only to the electric field itself and not the test particle. The electric potential can be calculated at a point in either a static electric field or in a dynamic electric field at a specific time, and has the units of joules per coulomb, or volts. There is also a generalized electric scalar potential that is used in electrodynamics when time-varying electromagnetic fields are present. This generalized electric potential cannot be simply interpreted as the ratio of potential energy to charge, however. Introduction. Objects may possess a property known as an electric charge. An electric field exerts a force on charged objects. If the charged object has a positive charge, the force will be in the direction of the electric field vector at that point. The force will be in the opposite direction if the charge is negative. The magnitude of the force is given by the quantity of the charge multiplied by the magnitude of the electric field vector. A net force acting on an object will cause it to accelerate, as explained by classical mechanics, which explores concepts such as force, energy, potential, etc. The electric potential at a point in an electric field is defined as the work done in moving a unit positive charge from infinity to that point. The electric potential at infinity is assumed to be zero. Force and potential energy are directly related. As an object moves in the direction that the force accelerates it, its potential energy decreases. For example, the gravitational potential energy of a cannonball at the top of a hill is greater than at the base of the hill. As the object falls, that potential energy decreases and is translated to motion, or inertial energy. For certain force fields, it is possible to define the potential of a field such that the potential energy of an object due to a field depends only on the position of the object with respect to the field. Those forces must affect objects depending only on the intrinsic properties of the object and the position of the object, and obey certain other mathematical rules. Two such force fields are the gravitational force field and the electric field in the absence of time-varying magnetic fields. The potential of an electric field at a point is called the electric potential. The synonymous term electrostatic potential is also in common use. The electric potential and the magnetic vector potential together form a four-vector, so that the two kinds of potential are mixed under Lorentz transformations. Electrostatics. The electric potential at a point or in a static electric field E is given by the line integral, where C is an arbitrary path connecting the point with zero potential to R. When the curl A, E is zero, the line integral above does not depend on the specific path C chosen but only on its endpoints. In this case, the electric field is conservative and determined by the gradient of the potential. Then, by Gauss's law, the potential satisfies Poisson's equation. Whereas the total charge density and AA denotes the divergence. The concept of electric potential is closely linked with potential energy. A test charge Q has an electric potential energy UE given by the potential energy, and hence also the electric potential is only defined up to an additive constant. One must arbitrarily choose a position where the potential energy and the electric potential are zero. These equations cannot be used if the curl A, EA permel 0, that is, in the case of a non-conservative electric field. The generalization of electric potential to this case is described below. Electric potential due to a point charge. The electric potential created by a point charge Q, at a distance r from the charge, can be shown to be where I micron 0 is the electric constant. This is known as the Coulomb potential. The electric potential due to a system of point charges is equal to the sum of the point charges' individual potentials. This fact simplifies calculations significantly, since addition of potential fields is much easier than addition of the electric fields. The equation given above for the electric potential are in the forms required by SI units. In some other systems of units, such as CGS Gaussian, many of these equations would be altered. Generalization to electrodynamics: when time-varying magnetic fields are present, it is not possible to describe the electric field simply in terms of a scalar potential V because the electric field is no longer conservative, is path-dependent because. Instead, one can still define a scalar potential by also including the magnetic vector potential A. In particular, A is defined to satisfy where B is the magnetic field. Because the divergence of the magnetic field is always zero due to the absence of magnetic monopoles, such an A can always be found. Given this, the quantity is a conservative field by Faraday's law, and one can therefore write where V is the scalar potential defined by the conservative field F. The electrostatic potential is simply the special case of this definition where A is time-invariant. On the other hand, for time-varying fields, note that, unlike electrostatics, note that this definition of E depends on the gauge choice for the vector potential A. One choice is the Coulomb gauge, in which we choose AAR equals 0. In this case, we obtain where I is the charge density, just as for electrostatics. Another common choice is the Lorentz gauge, in which we choose A to satisfy units. The SI unit of electric potential is the volt, which is why a difference in electric potential between 2 points is known as voltage. Older units are rarely used today. Variants of the centimeter-gram-second system of units included a number of different units for electric potential, including the apvolt and the statvolt. Galvani potential versus electrochemical potential. Inside metals, the energy of an electron is affected not only by the electric potential, but also by the specific atomic environment that it is in. When a voltmeter is connected between two different types of metal, it measures not the electric potential difference, but instead the potential difference corrected for the different atomic environments. The quantity measured by a voltmeter is called electrochemical potential or Fermi level, while the pure unadjusted electric potential is sometimes called Galvani potential. The terms voltage and electric potential are a bit ambiguous in that, in practice, they can refer to either of these in different contexts. See also, absolute electrode potential, electrochemical potential, electrode potential, gluon field, Lear copyright Nada Wichert potential, mathematical descriptions of the electromagnetic field, voltage, or potential difference, references. Griffiths, David J. Introduction to Electrodynamics. Prentice Hall. ISBN A0-13-800 Exer, Jackson, John David. Classical Electrodynamics. USA, John Wiley & Sons, Incorporated. ISBN A978-0-471-30932-1. Wanksness, Roald K. Electromagnetic Fields. Wiley. ISBN A978-0-471-81186-2A.